is that for pre?
So today we're going to look at 4.2. We're going to split this into two parts, and we're going to focus on graphing. Okay, so we're going to look at how we graph rational functions. And there's a big difference between graphing when the degree in the top is bigger versus when the degree in the bottom is bigger. It controls a lot of things about the graph. So that's kind of the two cases we're gonna split it into. All right. So remember that when we're graphing a rational function, that we have to be careful about holes in the graph. And we talked about it yesterday, and we've talked about discontinuities before that. If you have a common factor in the numerator and the denominator, then you can end up with what's called a removable discontinuity. That's the fancy word for a small hole in the graph. When you use a graphing calculator, you cannot see a removable discontinuity. The only way to find it is exactly what I've written right here. Factor. You have to factor your numerator and your denominator. So, let's take a look at this. Let's graph x minus 1 divided by x minus 1. Now, what value are you not allowed to plug in for x in this case?
1.
Right, you're not allowed to plug in 1. So that is definitely a value that's not in the domain. But the question then becomes, is it a vertical asymptote at 1? Or is it a hole at 1? Well, let's hit graph and see what happens. Okay, so we didn't see anything happen at 1. It just went right through it. But if you try to trace at 1, and you hit enter, it doesn't give you a value for y when x is 1. And if you go to the table and you type in 1, it's going to say error. So in that case, did we get a hole in the graph or a vertical asymptote? We got a hole. So if we were sketching something like this on a test, I'd be looking for you to draw it like that. Put the hole where it is in the graph, and then line going in both directions. And then again, on this one, be a hole. Make sure the hole is not filled in. It's empty. All right. How about this one? What value are you not allowed to plug in here? 1 again. Is it going to be a hole or a vertical asymptote?
Asymptote?
No, I think it's going to be the same thing because if you plug in for x, no, it'll be 1 minus 1, 0 squared, 0.
So it's going to be a hole, but I'm not clear on why again. Why is it going to be a hole and not an asymptote?
If we plug in 1 for x, it's 0, and 0 squared is the same thing, 0.
Doesn't have to do with plugging a number in. Yep.
Because you could factor out x minus 1 from both sides.
So if you write the top out, it's x minus 1, x minus 1. And in the bottom, we have x minus 1. All right, so keep going. What does all this mean?
So you'll be able to factor it out. And we said before that discontinuity can be found if the numerator and denominator can be factored out. So the top, they both cancel out. So 1x minus 1 on the top would be removed and x minus 1 on the bottom.
Yes.
Also be factored out.
So we have a common factor in the numerator and the denominator. That's why we get a hole. All right, common factor. So essentially what it's going to look like is the graph y equals x minus 1, almost, except there's going to be a hole at 1. So it's actually not a line, but it's almost like two rays going in opposite directions from the hole. Okay. So in both of those examples, we did not have a vertical asymptote. We had a removable discontinuity. And think of a removable discontinuity as a small problem. It's not even noticeable on a calculator. A vertical asymptote, that's a big problem, right? If you're trying to connect two parts of a graph and they look like this, say it goes like this and like this, that's a real big problem to try to connect those two parts of the graph because they're not even close to connecting, right? They're going in opposite directions. But if you've got something like this, that's pretty close to connecting. All you'd have to do is fix this one little spot, and then everything would be connected. So any question on why this would be really easy? And pretend like that's a little hole in the road, and you just patch it, fill it in, and now everything's nice and smooth and connected. Versus this, it's like you'd have to build a bridge between the two. They're not even close to connected. So any questions why this would be pretty easy to make connected if you just fix one thing, compared to the one on the left is not easy to make connected. Okay, so if all you have to do is fix this one little spot, what we can do is say, all right, we're going to use the regular formula that I gave you, like say this. We're going to use this formula to calculate every single x value except one of them. We're not going to use this formula when x equals 1. I'm going to tell you separately what to do if x equals 1. So I could say something like this, and then say, if x equals 1, then let y equal 1. So it's like a little exception to this formula. They use this formula all the time, except if you happen to run into the case when x equals 1, then just let y equals 1. So this is like patching the little hole. We're filling it in. I'm telling you to do something separate when you get to 1. But use this for everything else. If you can do something like that, that's called a removable discontinuity. All you have to do is redefine the function at that particular point and say, okay, use this formula most of the time, but if you run into the case where you have this certain value, don't use the formula. Do this instead. Okay? We're redefining the function at one particular point, which allows you to basically remove that discontinuity. Okay? But you can't do that with a vertical asymptote. Okay? Think of a vertical asymptote, it's like two cliffs and they're 2 miles apart. We're not even close to connecting them. Any question on that idea? All right. So, we're going to talk about how we can find the EBM. If you remember, does anybody remember what does EBM stand for? We used that back in chapter 3. Yeah. What's it?
End behavior model.
The end behavior model. So we know how to find an end behavior model for a polynomial. What is the EBM for something like this? What's the EBM there? Yeah, Nick?
Both sides going up.
That's describing the end behavior, but the model is an actual formula you could type in on the calculator.
Y equals x squared.
No, not in this case. X squared would not be the EBM.
Oh,
Yeah.
8x squared.
Can you say it again?
8x squared.
Nope. The EBM is not 8x squared.
Negative 9x cubed.
It's negative 9x cubed. Okay, the EBM is always the highest degree term. Well, when you want to find the EBM of a rational function, it's really pretty simple. All you have to do is find the EBM in the numerator. In this case, the highest exponent is first, and every other exponent is lower than the first one, because it says n minus 1 here. So they're going down. In the one I gave you, they didn't go down. That was the trick. You had to look and see where the highest one was, and it was in the middle. Generally not a good way to write a problem like that, but you need to check for that. So, highest degree term of the numerator is a sub n, x to the n. And the highest degree term in the denominator is b sub m, x to the m. All the other exponents go lower till you get down to the constant. And to find the EBM of the whole thing, okay, of f of x, all you have to do is divide the two EBMs that you have. Take the EBM in the top and divide by the EBM in the bottom. And remember, the EBM is really only used when you're looking at large values of x. It's only really applicable for large values of x. So if you look at something like this, and you plug in 2. Well, if you plug 2 into the whole thing, or you just plug 2 into this middle term, it's going to come out very different. Right? You're going to get a very different result. But if you plug in a billion, right? If you plug a billion into all these terms, or you just plug it into the one that's going to give you the biggest result, it's basically going to come out the same. Maybe you'll get a billion, maybe you'll get, the other way you do it, you get a billion 100,000. I mean, there's not much of a difference. Okay? So the EBM only applies when you're looking at large values. And if we wanted to take and divide the EBM in the top by the EBM in the bottom, we're going to end up with two variables that are the same. And most of the time, we're going to have different exponents. Anybody remember what you do with these exponents when you divide and your variables have the same base? Caleb?
Subtract them.
You subtract them. So you'll end up dividing the two numbers in front. You're going to have a variable, and you're going to subtract the exponent in the top minus the exponent in the bottom. That's how you find an EBM for a rational function. And when we look at really large values, we talked about this yesterday in 4.1. When you look as x approaches infinity, usually you do that to try to figure what out. Or you can look when x approaches negative infinity. When you look at what happens at either of those two directions, usually you're trying to figure out if your function has a what?
Asymptote.
What kind of asymptote?
Vertical.
Vertical is when we look for the zeros of the denominator. But
Horizontal.
horizontal.
Got to be one of the two.
So the EBM is basically used to predict the horizontal asymptotes, because the EBM will predict what happens at the ends of the function. And that's exactly what a horizontal asymptote is. What's happening at the ends of the function. So that's going to be one of the first things that we find when we want to do horizontal asymptotes. Find the EBM. Okay? All right, let's look at this one. All right, so EBM. Madison, what's the EBM of the numerator?
2x squared.
Yep, 2x squared. And Maddie, what's the EBM of the denominator?
3x cubed.
3x cubed. And now we want to reduce that as much as we can. So Lindsay, when I reduce that, what do I get?
2/3 x negative 1.
You could write 2/3 x to the negative 1, but what does that mean when you have x to the negative 1? Where would that x really be? Yeah?
1/x.
It would mean 1 over x, right? So it really means 2/3 times 1 over x, which comes out to what? Yep.
2/3x.
2 over 3x. And that's generally how we want to write it. So always follow your rules for negative exponents. If you end up with a negative exponent, it means it's in the bottom of a fraction. So we end up with 2 over x, 2 over 3x. Any question on that? Now, it says find the horizontal asymptote. So that's the EBM. Generally, when I ask you for a horizontal asymptote, I'm going to be looking for the equation. How should you always start the equation for a horizontal asymptote? Yep.
Y equals.
Should always start y equals. If you put x equals, you just told me vertical, so that's wrong. But it's y equals. And now, remember, to find the horizontal asymptote, look at what happens in the EBM as x approaches infinity, or negative infinity. So what happens to my EBM as you plug in a bigger and bigger number for x? Yep.
It gets smaller.
And what does it approach?
0.
It approaches 0. All right, if x was 1,000,000, you would have 2 divided by 3 million. A very small number. Now, will this EBM ever reach 0?
No.
What if I plug in 1 billion?
No.
No, it's still 2 divided by 3 billion. That's not 0. It's small. But the point is, it never reaches 0. Okay, any questions on that? All right. So again, step 1, find the EBM. Step 2, let x approach infinity in the EBM and tell me what number you get close to. In this case, it's 0. Let's look at this one. What's the EBM in the top, John?
2x to the 4th.
Okay. And what's the EBM in the bottom? Leah?
3x.
So when I simplify, what is my EBM? Yeah.
2/3.
2/3. Now, in that fraction, let x approach infinity. What happens in this fraction as x approaches infinity? Mm-hmm.
It's just a vertical or like a horizontal line. It's really great because there's no x.
So what number would I approach as x gets bigger and bigger in that fraction?
2.
2/3. Okay, there is no x. So our asymptote doesn't have, or our EBM doesn't have a variable in it. So there's nothing to plug in. It just is going to approach 2/3. Okay. Which makes sense because these terms basically disappear as you go towards infinity. I mean, taking the number like 500 and raising it to the 4th power totally overpowers taking the number 500 and squaring it. So these two terms control everything that's happening as x gets really big. And when you simplify the division of those two terms, the x to the 4th powers cancel. So all you're left with is something approaching 2/3. So if you plugged in 1,000,000 for x, you'd get an answer very close to 2/3. Not exactly, but pretty close.
Would you write it as y equals 2/3, or would
Yep.
you just leave that?
Nope, we're going to write it as y equals 2/3. So EBM. Questions on that one? All right. So, the first case we're going to look at for sketching is when the degree of the numerator is less than or equal to the degree of the denominator, just like the last two problems I gave you. The degree of the numerator is less than the degree of the denominator in example A, and in example B, the degrees were equal. We're not going to look at when the numerator is bigger until tomorrow, okay, but we're going to look at when the numerator is smaller or equal. So here are some general hints to graphing rational functions. They don't always all apply, depends on the problem. But if you can find intercepts, that's always helpful. Not every rational function has intercepts. Here's a graph with no intercepts. Never crosses either axis. So in that case, this step wouldn't help. But sometimes it will. Remember, to find the x-intercept, you let y equal 0. And to find the y-intercept, you let x equal 0. Just think of a coordinate on the x-axis. Right? That's the x-intercept. Any coordinate on the x-axis has a y value of 0. All right, next thing you're going to want to find are the vertical asymptotes. So we're going to find the vertical asymptotes by calculating the roots of the denominator. And how do we do roots? We have all kinds of ways. We talked all about that in chapter 3. Next, we want to find the horizontal asymptotes, and we're going to do that by finding the EBM. Then what we want to do, and we'll use the graphing calculator to help us do this, is we're going to look at what happens as you approach the vertical asymptote. Remember, you always approach infinity or negative infinity. Well, usually. So we're going to look at, all right, if we've got a vertical asymptote at 2, well, what happens if we plug in 2.001? We can't use 2, but we can get close to 2. And I want to see what would happen to the graph if I approach the asymptote from each side, from the right and from the left. And then we can double check everything with my sketch on the calculator. All right, so we'll go through as many of these steps as we can that apply in graphing the next couple problems. I think I have 3 examples left to look at. And they're all sketches. Okay, so that's pretty much it for notes. Yep. Okay, so it says sketch a complete graph. And what I would look for on a test is, did you find all the information to do the sketch? Did you go through all 5 of those things? All right. Let's start with the x-intercept. Can someone remind me again how you find the x-intercept? Did you write it out? Yep.
You let y equal 0.
You let y equal 0. So that basically means put 0 here. So to find the x-intercept, you have to make your fraction come out to 0. Well, what's the only way that a fraction can ever come out to 0? Yeah?
If 0 is on the top.
If you have a 0 on the top. So all I have to do to make this fraction come out to 0 is check when that happens. And when does x minus 1 equal 0?
When x is 1.
When x is 1, let's just make sure that doesn't cause us to divide by 0, because that's another problem. If you plug 1 into the bottom, would you be dividing by 0?
No.
No, then that's fine. So there is your x-intercept. So we're going to cross the x-axis right there. That's not enough to make a graph, but at least we have that. Okay, y-intercept. Y-intercept is when what?
When it crosses the y-axis.
And how do we find that?
X equals 0.
When x equals 0. So it should be pretty quick. When you fill 0 in the top, what do you get?
-1.
What about when you fill 0 in the bottom?
-6.
-6. So my y-intercept is at 1/6. Again, not enough to make a graph, but we're definitely going to draw the graph through those 2 points. Okay, so x-intercept, y-intercept. Let's find the vertical asymptotes. How do you find vertical asymptotes? Yep.
Finding the roots of the denominator.
Find the roots of the denominator. So x squared minus x minus 6. Okay. What can we do to solve that one? It's already a quadratic, so we're not going to have to do any kind of rational root theorem. What would be the easiest way if it works? Yeah? Yeah, let's try to factor it. And that does factor. Anybody see how it factors? Caleb?
X minus 3, X plus 2.
Yep, x minus 3, x plus 2. So based on that, what are my two numbers that would make the denominator 0, which will be my vertical asymptotes? Yep.
3 and -2.
3 and -2. Okay, so now what I want to do is sketch those on my graph. Right, so I'm going to put in a vertical asymptote at 3 and -2. So -2 right about there, and 3 right about there. Perfect. Okay, so I've got those. What else can I find? EBM. All right, what is the EBM in the top?
X.
X. What's the EBM in the bottom?
X squared.
X squared. And what does that reduce to? Yeah. What did you say it again?
1x.
1 over x, yes. Now, horizontal asymptote, let x approach infinity in that fraction and tell me what number my fraction approaches. Yeah, 0. So we have a horizontal asymptote at y equals 0. So I think we've found everything that we can really do by hand. Okay, but we've got all these different asymptotes. Now, I want to look at what happens as I approach the vertical asymptotes. Right, so at this point, I want to type that in. Not to graph it, but just to use the table. I could do this by hand, but it's faster for me to use the table. All right, so x squared minus x minus 6. So let's start with our vertical asymptote at -2. Can somebody give me a number that's very close to -2, approaching from the left? John?
-1.89.
That would be from the right.
Sorry, was it -2.1?
Even closer.
-2.01.
-2.01. When you plug in -2.01, or if you go even closer, you're at like -600. So just to the left of the vertical asymptote right here, you're way down. Okay, so on your graph, you're going to be way down. Okay, I can't even really draw how low it goes, but it's down. Now, let's try a number on the other side of the asymptote. What's a number very close to -2, but on the right side? Yep.
-1.99.
-1.99. And we're up at 60. Okay, we're up very high.
But you got that table?
Second table. So when we go to the right of the asymptote, it's up very high. Now, and also when you get to the table, you have to go to table setup and make sure your table setup is on ask for independent and auto for dependent, just like that.
And how do you get to the actual table again?
Second graph.
Oh, okay, thank you.
Okay, let's look at the other asymptote. It's at 3. Don't plug in 3. Can't do that. That's an error. But let's plug in a number very close to it, just a little smaller. What's a number? What would be a good number? Yeah, 2.99. And we're at -400. So when we go to the left of the asymptote, we're way down here. And what's the number just a little bigger than 3? Yep.
3.01.
3.01. I hit it a couple times, that's fine. Just to the right of 3, you're at 4,000. So you're way up here. Okay, so now we have to make a sketch. That's pretty much enough information. So remember, and if you want, you could get another point, like the edge of my graph is -10. If you plug in -10, you're at -0.1. Just a little lower than 0. I don't really need that point because I know what's going to happen, but if you want it, you can. Let's plug in +10. We're just a little bit above here. Right there. All right, let's start with the section in the lower left. We're going to have a graph that's going to be getting closer and closer and closer to that green dotted line. And it's going to get closer and closer and closer to that one. And those two have to connect. And the way they connect is kind of as a curve. So you're heading to the right, and then all of a sudden, it can't keep going to the right because it runs into that asymptote, and it ends up going down like that. It's going to be kind of the same thing in the upper right. It's going to stay very close to the asymptote, and then as you try to start heading to the right, all of a sudden, it runs into another asymptote that forces it to curve that way. And then in the middle, we've got 4 points that have to all be connected. We have to stay very close to this one, very close to this one, and go through the middle. So it's going to do a little bit of a curve in the middle. So it's going to come down, stay pretty close, all of a sudden curve, get close to that, and curve again.
That's pretty cool.
And that's your sketch. Sometimes it should be a little flatter in there than I maybe drew it, but if you hit graph, that's going to be a pretty good sketch that we just did. So you got your left section, you got your middle, and you got your right. And that's a pretty common pattern for these kind of graphs. 3 sections, S shape in the middle, and curves like that. All right. And all this data kind of helps you to get that graph, really. The asymptotes are good because they give you almost like a grid to draw your graph in. So we always want to get those.
And then how did you get the points in the middle again?
These were the intercepts.
Okay.
The X and the Y intercept.
Can you pull up the graph again from the calculator?
Can you just show again how to take or find the X and Y intercepts?
So that we're going to do another one, but the X intercept is when you make the Y value 0,
Yeah.
and the Y intercept is when you make the X value 0.
Yeah. Okay.
So it's just filling in a value and then solving. So we'll do another one. Let's see, I have this one, and that was it. That one is, so this one has linear in the top, quadratic in the bottom. Linear in the top, quadratic in the bottom. This graph is going to look almost identical. Okay. Let's do, if we have time, we can do another one like that. But let's do this one where it's quadratic in the top and the bottom. It's not actually that much different, but. Okay, let's go through. Vertical asymptotes. Someone remind me, how do we do those again? John?
The vertical ones, is that finding in behavior?
Nope, not
Or is
for the
that finding
vertical.
the zero?
Finding the zeros of
The denominator.
denominator. Okay, what can I do with that? 2x squared minus 5x equals 0.
You can factor the common factor.
Yep.
X.
Common factor of x. So 2x minus 5 equals 0. So where would my 2 vertical asymptotes be? Caleb?
Would be 0 and -2/5.
Negative and, yeah, I like the 0.
-5/2.
That's negative
No.
2.5, but it's not negative 2.5. Yep.
Positive 2.5.
Positive 2.5. 2 times 2.5 is 5. 5 minus 5 is 0. Okay, I'm going to graph them later. There's my vertical asymptotes. Horizontals. What do we find first that gives us the horizontals?
EVM.
EDM. What is the EDM in this case? 3 over 2. Now, let x approach infinity in that fraction, and what do you get? 3 over 2. So our horizontal asymptote is 1.5. Decimal is helpful when we graph, if you don't know that that's 1.5. All right, X Intercept. What do we do to find the X Intercept?
Set y equals 0.
Set y equal to 0. That means put a 0 right here. What's the only way that a fraction can equal 0?
The denominator's
The
0.
top is 0. So to find the X-intercept, set the top equal to 0. 3x squared plus x minus 4. All right, let's see if we can factor that. I hope. That would be a 3x and an x. We would need a 1 and a 4. And then we would need a plus and a minus. Let's check. 3x squared minus 3x plus 4x. What's minus 3x plus 4x?
X.
X. Perfect. All right. So x-intercepts. I get 2 of them. This is going to cross the x-axis twice. What's my first x-intercept? Yep. Negative what?
4.
If we plug negative 4 in for x in either one of those, we wouldn't get 0. Yep.
Negative 4 over 3. Or
Yep. Negative 4 over 3. And what's my other x-intercept?
1.
1. Okay, y-intercept. How do we find that one? Set x equal to 0. What happens if you plug in a 0 for x there? What do you get in the top?
Negative 4.
Negative 4. What do you get in the bottom?
0.
0. Can't do that. This graph will never cross the y-axis. Because you would end up with, what was it? 0, or no, negative 4 over 0. That's divided by 0. So no y-intercept. Okay, that's enough information to make our sketch.
And then the y-intercept, do you do the numerator or the denominator?
The y-intercept, you plug in 0 for x.
Oh.
So both.
Oh.
All right, so vertical asymptotes, 0 and 2.5. Let me make this a little bit easier to work with. 0, 2.5. So here's 0. We want to think about some values as we approach those numbers. Here's my y and y horizontal, 3/2, which is 1.5. And what else do I have? X-intercepts. Negative 4/3, that's negative 1.3. So, about right there. And 1. About right there. And I think I've used everything I figured out. Okay. What's the next step I do to get some more points? What am I going to use? Yep.
Plug it into the table in our graphing calculator.
Yep. I'm going to use the table, and I'm going to find as many points as I need to get a good sketch. So 3x squared plus x minus 4 divided by 2x squared minus 5x. All right. So let's think about our vertical asymptotes. We have 1 at 0. What's the number that's just to the left of 0?
0.001.
Left.
No.
That would be right. Yep. Negative 0.0001. and we're at negative 8,000. Okay, so just to the left, your graph is going to go way down. What do you think is going to happen just to the right?
Way up.
Yep, usually it's the opposite. So way up at 800. Okay, my other vertical asymptote is at 2.5. So don't plug in 2.5, you're going to get an error. Let's plug in numbers close to it. What's the number very close to 2.5, but to the left of it? Smaller. Yep.
2.499.
Yeah, let's go 2.499. And we're at negative 3,000 something. So way down here. And what's the number just to the right of 2.5? Yep.
2.51.
2.5. Let's go even closer.
1. Or 2.01.
Yeah, let's go like. And we're up at 34,000. Okay, so we're up very high. All right. So if you want to get one again at negative 10 and 10, you can do that to get the edges. Negative 10, you're at 1.1. So just about right there. And positive 10, you are at 2. About. So positive 10, we're at 2, sorry. Right. Okay, so it's going to have a very similar look to the last one. It's going to curve, it's going to stay very close to this asymptote, and then all of a sudden, it's going to curve down and keep getting closer to that asymptote. Upper right is going to do the same thing. Okay, stay very close, and then all of a sudden curve, and again, staying very close. And the one in the middle, this one's going to look pretty steep, all right? It's going to have a curve to it, but not as much of a curve as we saw before. It's going to come down, curve, and then do something like that. So I think that's what it's pretty much going to look like. Let's graph it and see. So there's our left section, middle section, and right section. Remember, when things start to get extremely steep, the calculator has a hard time drawing it. So it got very, very steep in this middle section, and the calculator didn't really know what to do. So it just stopped. Well, it should look more like what I did. And the same thing here. It got very steep on the left part, right? Or the lower left part. And that's pretty much what these graphs look like. Any questions on that? Yeah.
For the vertical asymptote, how did you get the 0 and the 2.5 from the x times 2x minus 5?
So we factored out the x. That was the first step. And then set each factor equal to 0 and solve.
Okay.
So you set x equal to 0 and you just get 0. If you set 2x minus 5 equal to 0, you would have to add the 5 and then divide by 2. And 5 divided by 2 is 2.5. Okay, any other questions on that? Any other questions on that kind of sketching? Does anyone want to see one more, or does anyone want me to just calculate part of something in one more? Like you want to see another UVM, or how to do another horizontal? Because we could do any part of this one that people are confused on. Is there anything that you're not sure about? X intercept, Y intercept, EBM, horizontal, vertical asymptote.
Do the mass break.
Can we do a mass break? Yeah. Alright, so that's the homework for tonight. Page 234. 1 through 7, odd. 9 to 12, 15, 17 to 22, 23 to 26, 29, and 33. They're not all sketching. I think some problems just say, like, find the horizontal asymptote, find the vertical asymptote. So they're not off stage.